Yeah, we are very happy to welcome Nadav, Meir, which is going to talk about structural Ramsey theory. And there was a mistake in the title, right? In the one that I
It
sent.
wasn't a mistake. I'll refer to it. No, it's
Okay.
It wasn't it was my mistake. Yeah, it wasn't a mistake.
So please welcome Nadav Meir.
Thanks. Sorry. Yeah. So regarding the title, so actually, I guess I thought about it, and it's kind of like so there is this paper by Krzysztof and Anand with a slightly similar title, which goes like a model theoretic perspective, and I wanted to pay tribute to that. And then I thought actually this talk, while it's more of a model theorist's perspective rather than a model theoretic perspective, and yeah, maybe I'll talk a little bit about what I mean by that in the future, but for now I'll leave you intrigued, I guess, or baffled. So yeah, without further ado, let's start by just recalling a few of the definitions of Ramsey theory, because I think I haven't noticed anyone in the seminar doing that before this talk. So whenever I say an ultra-homogeneous structure, I mean that every isomorphism between finite substructures of it extend to an automorphism of it. So that also includes not necessarily countable structures, right? But in this context, when we say ultra-homogeneous, we mean with respect to finite and partial isomorphisms. Yeah. So, right. So an amalgamation class is, now I want to make a distinction because it's not necessarily, this will not necessarily be a countable amalgamation class, but just such that it is closed under isomorphism substructures, has the joint embedding property and the amalgamation property, which I'm sure most of you are familiar with. So the joint embedding property just says that whenever I have two structures in the class, there is some structure in the class that can embed both, and the amalgamation property essentially says that I can amalgamate two structures over a common substructure. So whenever I have two embeddings of a given structure into two different structures, there is an embedding of the two into a larger structure such that the embeddings commute, right? And something that may be a little bit some of you may be less familiar with, but I guess most of you probably are, is the strong amalgamation property. So we say K is a strong amalgamation class if it has this property, saying that we can, in the amalgamation property, we can choose the D and the embeddings above such that the only intersection happens essentially when it's needed to be the intersection. So the intersection of the images of A and B is precisely the image of the common structure C. So any questions up until now? I'll be looking at the faces, I guess not, okay. Great, so we know the theorem by Fraisse from 54 that says that the age of a countable ultra-homogeneous structure is an amalgamation class, which is countable up to isomorphism. That's the easy part. The harder part is actually constructing this Fraisse limit, taking an amalgamation class, which is countable up to isomorphism, and then constructing. So there is an ultra-homogeneous countable structure such that its age, so the finite substructures that are embeddable inside that structure, is precisely that class. And such structure is also unique up to isomorphism, and this is what we call the Fraisse limit of the class. And there is a folkloric lemma that I guess was probably known beforehand, but the earliest possible occurrence that I found is but from a book by Peter Cameron about permutation groups, and he says that the age of a given countable ultra-homogeneous structure, or equivalently an amalgamation class, it's a strong amalgamation class if and only if M is algebraically trivial, meaning that the algebraic closure operator is trivial on finite sets, right? Okay, so let's go very quickly through examples. So the finite graph, sorry, there's a typo, correspond to the random graph as the Frisell limit. Finite linear orders correspond to the dense linear order. Finite equivalence relations correspond to the structure which has countably many countable equivalence relations and finite equivalence relations. So this is where I want to kind of break a little bit the strong amalgamation. So here we have algebraicity, right? Finite equivalence relations such that the equivalence class is of size at most 10, let's say. That's an amalgamation class, not a strong amalgamation class because it has algebraicity. It has doesn't have the strong amalgamation property, but this corresponds to countably many equivalence classes of size 10. Okay. And also you can see that finite convexly ordered equivalence relations are also an amalgamation class. Yeah, actually a strong amalgamation class. But if we take finite ordered equivalence relations, not assuming that the order is convex, or more precisely that the equivalence classes of the equivalence relations are convex.
So Nadav, what do you mean by these last two examples exactly?
So here, in both, I take the language is a language with two relations, one which is an equivalence relation, one which is a linear order. Okay. In the first one, we assume that the equivalence relations are convex, namely that the equivalence classes are convex with respect to the order, and in the other we don't assume it. So the other one, the last one, is more random, you can say, than the other.
What does the word finite? Then what does the word finite mean here?
Finite is just it's because it's the class. I mean the class of all finite structures, right? I'm not talking about the Frisell limit. I'm talking about the class. Okay, but yeah, the Frisell limit will be just the generic, you know, like. The generic countable structure which has this as its age. So in the last example, you can think about just a linear order and a random equivalence relation in a sense. And in the second to last example, you can think about just countably many countable equivalence relations, such that you have the order, and the order kind of orders the equivalence relations, and then within the equivalence classes it also orders the equivalence classes, and both of them are a densely linear order without endpoints. Is that clear?
So do you have several equivalence relations or just one?
No, just one. So yes. in both, the language is just one equivalence relation and one order. Okay, in the first one, the equivalence classes are convex, and in the last one, they are not necessarily convex. I mean, yeah, just generic. Is that clear? No, any questions on Itai? Is that clear?
Yeah. The confusing thing was just finite and relations.
Okay. Okay. Oh, right. Yeah, relation, ordered equivalence relation, right? One equivalence relation. Sorry. Yeah, actually, interestingly, I mean, you can think about it, but if you take any number of equivalence relations on an ordered set, you can do that, and that would be an amalgamation class. But if you take two equivalence relations and you assume that they are both convex, so that's not an amalgamation class. But anyways, okay. Now we move into Ramsey theory, which I guess at least less of you are familiar with these definitions, so I want to go over them. So, and what I'm going to say is like, this is like my perspective of, so maybe okay, so the definitions will be maybe a bit non-standard, but they are equivalent in any sense to what people, combinatorists, do in Ramsey theory. But anyway, given two structures, A and B, usually we consider finite structures, right? So we look at this binomial coefficient B over A is just all of the embeddings from A to B. Okay, so we assume A and B are in the same language. And if I have a class of finite structures in a given language, so for each A in that class, for every structure in the class, the Ramsey degree, we call it TA of A, is in K, right? So always with respect to the class in which it lives, is the minimal number T, which could be Aleph 0, but so either finite or Aleph 0, such that the following property holds. So for every natural number n and every other structure B in the class, there is some bigger structure in the class. It has to be bigger, such that whenever I color the embeddings of A inside C in K many colors, there is some embedding of B into C, such that this set, so this is essentially like the induced coloring of the embeddings of A inside B, is colored by at most T colors. Okay, so if all of these, if this is fine, this T of A is finite for every A, then we say that this class has finite Ramsey degrees. And if it is actually equal to 1 for every A, then we say that the class has the Ramsey property. And here we call it ERP for the embedding Ramsey property, as opposed to the structural Ramsey properties, which I don't really want to get into. But just as a side note, this is what, like, if you would ask anyone who does contemporary Ramsey theory from a combinatorial point of view, you say Ramsey property. This is the Ramsey property that is like considered.
So Nadav, you're not in the definition. You're not asking that that B contains a copy of A or C contains a copy of B or anything like that.
I'm not assuming it, but I think like it follows, yeah, because you say for like. So the condition is trivial for B that does not contain A all the time. So obviously the only thing that you want to check is for B that contains A. And then, yeah, and then you need some C such that there is some coloring of this binomial coefficient, right? And there is some embedding of B to C. So you see it kind of follows from the definition. So you don't really need to assume it, but anyway, it's just kind of nonsense. But yeah, it's equivalent. Okay, is it clear that it is equivalent?
Yeah, I hope so. Yes. I mean,
yes.
Can you say something about what this ERP means, really? It's quite...
What do you mean by what it means? Like,
can you say something? Can you give some intuition of what's going on? What does it mean if TA equals to 1?
So if TA equals to 1, so essentially let's try to draw this, okay? So the drawing goes like, let's do this. I have like, I don't know, like orange maybe. So I have some structure A, and I have some superstructure of AB. Okay, so if B does not contain A, then A. So I have some structure A. So for every number K and for every B that contains A, right, there is some bigger structure C such that whenever so C contains, let's say, many copies of, or several copies of several embeddings of B inside C, and there are several embeddings of A inside C, right? So it could be that there is like one copy here and so on, and here a copy of A, and inside B there are several copies of A, and so on. So now the existence of such C, so the Ramsey property says that there is the existence of such C, such that whenever I color A, the embeddings of A inside C in any finite, in K many colors, okay? So C actually depends on K and on B. This is something that needs to be noted. So whenever I color C, the embeddings of A inside C in K many colors, there is some B such that all of the embeddings of A that are part of an embedding of B are colored in the same color. So I guess you can think about it like, let's look at essentially the classical Ramsey theory. You can translate it to saying that the class of finite linear orders has ERP. How can you see that? So for any finite linear order A, let's say, and for any sorry, how does it go? Okay, maybe I will get confused by this. So whenever I have some finite linear order A, and then I choose some K and some B that contains A, so something like this, maybe. Yes, yeah, so so there is some C such that, yeah, so there is this version of the Ramsey theory that says that that there is some finite linear order C, and such that whenever I color it in K many colors, there is some linear order such that it is monochromatic in the sense that so here actually all of the embeddings of A are the same as just taking subsets of B which are of the same size as A, because we have the linear order, then they are all of the same color, I guess. You can say, yeah. Is that kind of does that give some intuition? Not so much. Yeah. So let me think about it a little bit.
Isn't it the case that for graphs, the standard Ramsey theorem is just take A to be an edge?
Yes. Okay, let me think about it. But here we have this is the embedding Ramsey property. So graphs do not have the embedding Ramsey property, but ordered graphs do. So, yeah, right. Okay, so that's exactly it, right? So so thank you, Asaf. So essentially right. So the classical Ramsey theory for graphs is the one that you take, you take this structure A to be just two dots. So just subsets of size 2, and then you say that there is an edge if they are colored in one color, and there is no edge if they are colored in a different color, or you can color them in k many colors, right? By induction, whatever. And then the Ramsey theory says that there is some
Nadav, what structure are you looking at here?
So now,
yeah.
Now, I'm claiming, let's say that there is, let's say that we are talking about the classical Ramsey theory that some of us learned in our undergraduate studies, that says that for whenever I have a finite, so yeah, so there is.
It's just complete graphs.
Sorry?
The class K would just be complete graph.
No, but I want to take it as an analog to ERP, to the embedding Ramsey property. So the embedding Ramsey property is the same as saying that taking A, I'm saying that the Ramsey theory, the classical Ramsey theory for graphs, the one that states that for every natural number n, there is a bigger natural number m, such that whenever I color a set of size m, the subsets of size 2 inside the set of size m in 2 colors, there is a monochromatic set of size n, the little one. So this is exactly saying that the Ramsey degree here in our definition of a structure of size 2 is 1. So yeah, and yeah, because you color like structures of size 2 they are corresponding to whether you color it as which color you assign to edges of the graph. But then essentially, if you look at ERP for in general, for let's say linear orders, okay, then this is the same as the Ramsey theory, just for any hypergraph that you take. So in this case, if A is of size 1, then this is just the pigeonhole principle. If A is of size 2, then this is the classical Ramsey theory for graphs, and if A is of size 3 or 4, etc., then this is the classical Ramsey theory for hypergraphs.
Yeah, Nadav, there is a comment in the chat, I think, which is relevant.
I don't see the chat. How do I see that? Oh, okay.
I was just trying to give an alternate explanation because I'm also used to that, but that's all.
Maybe we can come back on the intuition at the end of the talk and move on. it's taking a bit of time.
Yeah, okay, thanks. So yeah, this is, I think the comment in the chat exactly says what I was trying to convey, even though I didn't prepare myself. Yeah. So, okay, but putting that aside, actually, we are not going to talk almost at all about intuition behind the combinatorics of it, precisely because of this celebrated results by Ketrick, Pestov, and Todorchevich from 2015, and they are saying that if M is any countable ultra-homogeneous structure, so for element of an amalgamation class, then the age of it has the embedding Ramsey property or the Ramsey property, if and only if the automorphism group of that structure is extremely amenable, meaning that for every compact Hausdorff space, every continuous action of that automorphism group has a fixed point, and here the automorphism group is considered with a point-wise convergence topology, as we probably all know, and the continuous action is just like this, an action that is continuous. Right, and a fixed point is just a point that is fixed by all of the elements of the automorphism group. So yeah. Okay, so and
Nadav, remind me, this also implies that M has that there's a unique, that it's rigid, that there's only, right?
Precisely what we are going to prove in the next slide. So yeah, I mean, so essentially this is something that was kind of like in their paper, they dealt with it a little bit the other way around. So they assume that there is a linear order, but yeah, actually you can, I guess now it's more well known in this way, and then proving from that there is always an invariant linear order on the structure. So how do we see that? We just consider the set of all linear ordered structures as a subset of this power set, right? And this power set is and this is a closed subset of a Hausdorff compact space, right? And then we consider the natural action of the automorphism group of M on the linear orders. So described like this, but without even saying, I think one of you would be able to imagine just what the natural action is. And this is a continuous, and therefore it has a fixed point. So this fixed point is an invariant linear order under the automorphism group, right? So this is what you were referring, Itai, and actually in our recent work, Krzysztof and I, we proved that that this linear order is actually possibly infinite, but it's a Boolean combination of relations in the language and not including equality. Okay, so this is kind of a crucial step that is technically needed to prove other stuff. Right. So
but wait, Nadav, here you assume everything is countable, right?
Here I assume everything is countable.
Oh, and also in the proposition.
Yes, but in the proposition, I only need to assume that it is ultra homogeneous.
Right, instead of like, as opposed to finite language, which is what usually.
Yes, I mean, yes, not necessarily. The language can be arbitrary, but under assumptions of ultra homogeneity, then this follows. Actually, yeah, countability is not needed here, but we will see that in a later slide. This is the work of Krzysztof and Anand. So, but before that, we go to that a little bit about kind of the importance in the area with regards to other areas. So there is this conjecture that has been open, you see, for some time now by Podilsky, Pinsker, and Todorchevich, that says that every ultra-homogeneous countable structure in a finite relational language, so this is like a very restricting assumption, kind of like in the Thomas conjecture, if you recall, which we are going to see. Actually, it's here. So has a precompact Ramsey expansion, meaning that it has an expansion to an ultra-homogeneous structure M star in a language L star, such that M star has ERP, so it has the Ramsey property, and every finite structure in A, or equivalently every structure in the age of M, right? The set of expansions of it to the age of M star is finite. So actually, Zucker showed non-constructively and then constructively, Lionel Van Zee showed it, that for every countable ultra-homogeneous structure, it's equivalent to have finite Ramsey degrees and to admit a precompact Ramsey expansion. Okay, and why is this? How does this relate to the conjecture by Thomas, which is open for over 30 years now? So the conjecture is that every countable ultra-homogeneous structure in a finite relational language has finitely many reducts up to isomorphism. So essentially, conjecturally, the plan of kind of hope to prove the Thomas conjecture, or at least see where it breaks down, is saying, okay, so the conjecture is that every countable ultra-homogeneous structure in a finite relational language admits a precompact Ramsey expansion. And this and now moving to a precompact Ramsey expansion, we can prove the Thomas conjecture, restricting to structures which have the Ramsey property. And if the expansion has only finitely many reducts, obviously also the reduct has finitely many reducts.
Nadav?
Yeah.
Is it obvious also that there is a Ramsey expansion without the precompactness assumption?
Well, yeah, I guess if you just, let's think about it for a second. I think like if you just name, like give names for like adding unary predicates, like many unary predicates, and then adding a linear order to it, I think that would be always Ramsey. Yeah, because then there is only like one embedding of each structure into another structure, right? Okay. Is that clear?
Sort of, yes.
Yeah, so just, yeah, adding like disjoint unary predicates, each has only like a singleton, and then adding a linear order. Actually, you don't need the linear order. It's kind of, yeah, but anyway. Yes, so I guess it's kind of clear. So yeah, now let's go look into it from a model theoretic point of view now. So now we are moving on to presenting work by Krzysztof and Anand. So now we are talking about the structure, any structure not necessarily countable or ultra homogeneous. And now we need to tweak a little bit the definition of what is a finite, what is this binomial coefficient. So instead of all of the embeddings, we take we take a tuple in M and a finite subset B of M, and then we take this binomial coefficient to be all of the copies of A bar in B via some automorphism of M. Okay, so now I guess it is clear that if the structure is ultra homogeneous, then this is the same definition, because every finite isomorphism extends to an automorphism, right? So, oh, sorry, this should be M. It's a typo. If I have a tuple M, then the Ramsey degree is again very similar to what we defined here, the some T of A, such that for every coloring K, in K many colors, for every K and for every finite B, there is some finite C, depending on K and B, right? Such that whenever I color the automorphic copies of A bar in C, then there is some B copy of B inside C, such that this coloring of B takes at most T many colors. So I guess, well, not a lot of intuition, but just seeing that this is like a very analog or generalization of the original one, right? This Ramsey degree, because if we replace it by what we said earlier for ultra homogeneous, it's the same, and we can define the same exact properties, having finite Ramsey degrees and having the Ramsey property.
What is K here?
What? Yeah, sorry. K should be M. That's a typo. This should be This should be. Sorry, this thing. This should be M, and this should be M. Sorry, it's a typo. Yeah. Yeah, this is M because it's a, yeah. In the other slide, it was K, and I didn't change all of the instances, so I'm sorry about that. Anyways, so there is this theorem that is generalizing the KPT correspondence. So for Krupinski-Pillay, it's the KP correspondence, I guess, saying that the following are equivalent. M has ERP in this new sense, and the automorphism group is extremely unmeanable in exactly the same sense. Okay, so and in exactly the same way, we have that the automorphism group is that there is an auto M invariant linear order, and also if M is ultra homogeneous, so this invariant linear order is a Boolean combination of relations in the language, but now dropping the assumption of countability. Yeah, I see now that Nick Ramsey approves of what we discussed about naming every element with a constant. So yeah, that's sorry, a clearer way of saying what I meant to say. Okay, so now we are moving to the next level, which is elementary embedding Ramsey property, and we say that a theory now T has the elementary embedding Ramsey property if a monster model of T has the embedding Ramsey property in the sense that we discussed now. And there is this theorem by Krzysztof Krupinski, Jungkook Lee, and Slavko Mokonia from 2020 plus, meaning submitted, not published, right? So so the definition of EERP does not depend on the monster model. Moreover, it suffices to consider an Aleph-0 saturated, strongly Aleph-0 homogeneous model. So any one you take, it's equivalent. So as a corollary, obviously, we get that if one has an extremely amenable automorphism, then any other has an extremely amenable automorphism, right? And now, I guess I have like very little time, right? Like 10 minutes. So let's see what, okay, I'll dive into it very, very quickly. So now a question that arises is whether these definitions are actually equivalent or not. So the answer is actually maybe what do you think is,
Which definitions are equivalent?
Yeah, so like, okay, so let me phrase the question really rigorously. So the question was that if I take an ultra homogeneous structure, okay, countable ultra homogeneous structure, and it has ERP in the classical sense. Is it necessarily true that its theory has EERP? So equivalently, is it true that if I take a monster model of it, it has also an extremely amenable automorphism group, or it has ERP as well? What do you think, Itai? Just say yes or no, just to
Yes,
get like.
I think yes.
Okay, great. So the answer is no, actually. And for that, unfortunately, I am diving into a subject that I thought would be behind me by now, but it's so like so useful, which is this lexicographic product to construct these kinds of examples in many areas. So the lexicographic product of two structures is just taking, so for now we assume there are no unary relations, okay? No unary relations, no constants, just binary plus. So, so we take the two structures, we take the Cartesian product, and we take something that is kind of like generalizing the lexicographic order. So if two structures have the same first coordinate, we ask what happens in the second coordinate. If they don't have the same first coordinate, we ask what happens in the third coordinate. So it looks something like this. We have like this triangle product square, and then so we have 3 copies of this square, and then we add relations between the copies of the square as in this triangle. And also we can take something more colorful like this, and we can add some equivalence relations saying that they have the same first coordinates, sorry. Okay, and now, so this is the finite lexicographic order, and now we can take also.
So what are A and B, sorry?
A and B are just, so AB is a tuple inside the Cartesian product, M times N. So A is an element from M, and B is an element from N, right? Always when I take Cartesian product, right? And now, so it is clear how we can, so we can iterate it finitely many times, like this is this, and then take a product of this, and also add equivalence relations. So the question is, what do we do with infinity? So for infinitely many equivalence relations, we kind of look at this and kind of like imagine that this is a tree of structures. And then we can ask, okay, so we have the branches of the tree, and we ask what happens between two elements. So let's say we take this element, and we ask what is the relation between them. So we go to their meet in the tree, and the meet in their tree in this structure. So in this structure, we take the successors, and we see that they are connected with a blue edge. So these two branches will be connected in the infinite structure by a blue edge. And this is what we are trying to generalize with this construction. So we assume that our tree is like omega to the less than omega. So it looks like an infinite branching tree. And then we take a family of structures indexed by the tree. And then we ask, okay, so the product is a structure of on the branches of the tree. So the branches of the tree here is omega to the omega, right? This is the branches of the tree, omega to the less than omega. And what are the relations? So between, let's say, two branches, we look at their meet, and then we ask what does the structure in the meet think about the successors with respect to each branch. And then that is the relation between the two branches. So it's enough to think about binary relations. wouldn't want you to complicate too much about thinking about non-binary relation, but anyway, because this product now, the branches of the tree, if we take a countable product of countable structures, right, it turns out to be something that is uncountable, right, because it's omega to the omega. So because of that, we take a dense substructure, and we can always see that whenever I actually, if we have, so maybe, is it clear, this definition, before we move on to the result about this definition? If there aren't any questions, then I'll move, yeah. So, so if on each level the structures are isomorphic in the tree, and they are all countable and ultra homogeneous in a countable language, then there is a unique countable dense substructure, and this dense substructure is ultra homogeneous, and actually you can see that not only is it ultra homogeneous, but if each of the structures have the embedding Ramsey property, then first of all, let's look at the classical product. Okay, so in the classical sense, with these equivalence relations, so a product of two structures with the embedding Ramsey property has the embedding Ramsey property. Why is that? Just by the property of the automorphism group, because the automorphism group of this product is exactly the Reith product of the morphism group M and the automorphism group of N. So a Reith product of extremely amenable groups is extremely amenable. You can do that as an exercise. And then actually you can see that this infinite product now, the age of it is just the union of the finite products, an ascending union of the ages of the finite products. And it's, if you think about the definition of the Ramsey property, it would be pretty obvious that an ascending union of classes with the Ramsey property has the Ramsey property. So this actually has the embedding Ramsey property. Okay, and now with this, if we can find an example of something that has the embedding Ramsey property, but not the elementary embedding Ramsey property as countable ultra homogeneous structures. Yeah, such that it has the embedding Ramsey property.
But Nadav, anyway, this example would not be in a finite language, right?
No, of course not in a finite language.
Because then it is because then I think it is clear that it's there.
Yes, that's an excellent comment. What you are saying, in a finite language, it is obvious because a countable. Yes, so thank you very much.
Because of a quantified elimination.
Yes, of course, that is what I wanted to say. Because if we have an ultra homogeneous countable structure in a finite relational language, then it is obviously also Aleph0 saturated, and also strongly Aleph0 homogeneous by quantified elimination. So obviously that won't be an example. So in order to think if this is true, we need to go into infinite language, and this is kind of a candidate. And for that, we take this infinite product such that in each level we have a different order. So for every I in omega, we have a different order indexed by I. And then we take the structures to be densely ordered according to the corresponding I, right? And then we take the product of all of this. So if we take now a countable dense linear order, it has ERP, but it is not saturated. It is not Aleph0 saturated. Why? Because for example, if I take the type over a singleton that says that there is another one that is not equal to it, but it is equivalent to it in all of the equivalence relation, equivalent 0, 1, 2, 3, and so on, so kind of equivalent infinity to it, then this type is not realized, right? So, but in order to realize it, we need to expand each of these infinity equivalence relations to be blown up to an infinite set. So this is exactly actually also characterized by an infinite, a lexicographic order. So it's just taking the product of D with just an infinite set with no structure. So it's kind of like taking this tree and so on. And then this, if this is D, then in each terminating branch, we blow it up by an infinite set. So this will be actually a strongly Aleph-0 homogeneous and Aleph-0 saturated. And maybe someone can say to me why this structure does not have the embedding Ramsey property. So it's because actually it does not admit an invariant linear order, right? Because we have these in X, there is no structure. It's infinite with no structure. So any permutation of like this inner X can induce extends to an automorphism of the whole structure, but then there is no linear order that preserves this, right? So yeah, that is kind of like the embedding Ramsey property prohibits such like cliques, let's say, or anti-cliques, or whatever you would call these kinds of pockets where the automorphism there is like the symmetry group. Okay, yeah, so that's what we said. Okay, so I guess now I don't have like any time, but let's see how much, yeah, so I guess just presenting briefly the results that we had, because I talked about the fact that this is like a model theorist's perspective, but actually the results that we have, they achieve actually results in the classical combinatorial Ramsey theory for really for actual like Ramsey classes and generalized several and unify several well-known results, but I won't be able to get into it, but I'll just say that like these results follow from two results that we did. So one is like generalizing the Ramsey full product theorem, and the other is the Ramsey property for what is called free superpositions. So the full product is just given structures MI indexed by an index set I, such that all languages are disjoint. We can take the structure on the Cartesian product, just saying that the relations behave such that the projection preserves the relation. So you can think about, if you think about two, you can think about kind of a box. So you can think about kind of a box if you think about the product of two structures, and here you have M1, and here you have M2, and here you have all kinds of relations, and here you have all kinds of relations. So when you ask what is the relation between this and this, so if the relation is in L2, you project onto M2 and ask what is the relation here, and if the relation is in L1, you project onto M1 and ask what is the relation here. So there is this classical theorem called the full product Ramsey theorem, that says that if I take a product of two structures, which has Ramsey property, then the product has Ramsey property, and we extended it to the infinite case. Okay, I'm not going to go over the proof, or it's just actually it uses the Krupinski-Pillay result about the extreme amenability of the automorphism group, regardless of whether it is countable, because this product ends up as an uncountable structure. So that is kind of the case. And also, if you are familiar with this free superposition, some people call this a free fusion, even though not free fusion in the sense of Wrocław, something completely different. It's just if I take classes, so let's say two classes, and their free fusion is just, and they are in these joint languages, then the free fusion is just the class of all finite structures, such that reducing to either language results in a structure in the appropriate class. Then you can extend it to an infinite class. Now, also, it's a problem because this class is not countable. So it's not necessarily the case that it has a Frese limit, because Frese limits only occur for, or only necessarily occur for amalgamation classes which are countable up to isomorphism. But regardless, we proved this theorem assuming the strong amalgamation property. If each of these structures has ERP, then all of the free superposition of the infinite free superposition has ERP. So this generalizes results by Bodievsky and Sokic, 2015. Sorry, not 215, obviously. Yeah. And I guess that's it.
Yeah.
So.
Thank you, Nadav. So are there any questions in the chat? Or here in the room?
See.
Yes, I have something
Okay.
to say. Yeah, so I'm not a model theorist, but I like to look at those things in the language of category theory. Sorry, it's kind of difficult for me to talk because I have some sound problem with my mic, but I have an echo in my ears. Okay, the ERP can be expressed only in the language of category theory.
Sorry, I didn't hear the last two words.
Also, what did you say?
I didn't
Can you
hear
speak
the
a
last
bit
sentence.
louder?
Oh, okay. Okay. Do you hear me currently?
Yes.
Yes.
Okay, so what I said is that the ERP can be expressed in the language of category theory. So you don't need to your objects to be actual structures. You don't need to morphism to be actual embeddings, etc. In this setting, you have a KPT correspondence, which has been proved recently by Masrovich. There is a recent paper that appeared on an archive that generalizes the usual KPT correspondence and also the Krupinski-Pillay correspondence you mentioned. And so here you have plenty of operations on classes that actually use what are the objects of the classes, the fact that they are structures. I wanted to know if you thought there were operations on categories that actually reflected what happened when you apply these operations on classes of structures. Like, do you have, for example, an operation that takes two categories and maps them to a new categories such that if your two categories are classes of structures, then the result is their lexicographical product, for example. I think it could be interesting to look at it.
Yeah, okay, I haven't thought about it, but yeah, it could be very interesting to look at.
Yeah, what makes me think about that is that I've seen recently, but I haven't had time yet to read them. that there are papers by Maslovich where he considers operations on categories that preserve the Ramsey property. So I was wondering if maybe they could be the same as yours, but expressed in a different language.
Yeah, I guess I don't know. I haven't looked into it really, but it's a good good point actually. Now, yeah, if you mentioned it, so we are now also extending this operation of this free superposition also to theories. So that's our set as model theorists perspective, right? So maybe also that could be generalized to the category sense. I don't know, but
I guess so, yeah.
Yeah. But thanks for the.
There was a question of Nick also. Did you have a question? Are you still here? Okay, Nick left. So Diclé, there was a question.
Sorry, are you asking me?
No. I think in the there was other people that raised hands to ask questions.
No, I haven't. I did it accidentally. Sorry.
Ah, okay. Alexi, did you have a question?
No, me neither.
Okay. So there is a question of John. Okay. So any other questions? Okay. So,